Picture the largest thing that has ever existed, not a star, not a galaxy, not a galaxy cluster the size of a city-sized thought experiment. Something so vast that if you compressed the entire observable universe into a room, this structure would stretch from one wall almost to the other. And until very recently, until a handful of overworked scientists pointed the most powerful telescope ever built at a smudge of sky no wider than 3 full moons, we had never properly seen it. It has no name most people know. It has never appeared in a school textbook. Yet without it, you would not exist. Your galaxy would not exist. The periodic table, every element heavier than hydrogen, none of it would have clumped together into anything at all. This structure is the reason matter has an address. It is the skeleton on which the entire visible universe is hung. It is made in part of something we cannot see, cannot touch, and have never once directly detected. And in the span of 18 months between the winter of 2025 and the spring of 2026, 3 separate teams of scientists on 3 different continents using 3 different instruments mapped it, photographed it, and traced it all the way back to when the universe was less than 1 billion years old. This is the story of the cosmic web, and it is one of the most consequential series of discoveries in the history of cosmology. There is a map you carry in your head of where things are. Your home sits in a street. The street belongs to a neighbourhood. The neighbourhood folds into a city, which is cradled by a country, which rides on a continent, which floats on a planet, which orbits a star, which wanders through the outer arm of a galaxy containing roughly 300 billion stars, which itself belongs to a group of 54 galaxies, known as the local group, which is gravitationally bound to the Virgo cluster, which is merely one node in a supercluster called Laniaceas, spanning 520 million light-years in diameter. That is your cosmic address, written out in full, and most people never get past the first line. But even Laniakea is not the whole story. It is, in fact, a single neighbourhood within a neighbourhood within a neighbourhood on a map so large that the map itself has a shape, and that shape is neither random nor uniform. It is a web. Look at the universe at the largest observable scales and something extraordinary appears. Matter does not distribute itself evenly. It does not scatter like grains of salt shaken across a tabletop. It clusters into dense knots connected by long, thin, luminous threads, which are themselves separated by enormous cavities of near-perfect emptiness. Imagine the most elaborate spider's web you have ever seen. Then imagine it hanging not in a garden, but across billions of light-years of space, each strand made not of silk but of hundreds of thousands of galaxies, each intersection glowing with the concentrated light of stars beyond counting, each void so empty that a single cubic meter within one contains, on average, less than 1 atom. That is the cosmic web. It is, to my mind, one of the most viscerally extraordinary features of reality, the fact that the universe has a shape, and that shape is not a blur or a smear or a grey uniformity, but something that looks almost alive. It looks almost biological. If you set the image of the cosmic web beside a microscopy image of neurons in the human brain, the resemblance is sufficient to stop you mid-breath. Nobody planned this. Nobody built it. Gravity did. Dark matter did. Time did. And the result is something so structured, so intricately patterned across scales of hundreds of millions of light-years, that it reads less like physics and more like architecture. The technical name for this architecture is large-scale structure. Cosmologists divide it into 4 components: filaments, the long threads of matter; walls or sheets, the broad planar surfaces where filaments intersect; clusters and superclusters, the dense knots at the junctions of multiple filaments; and voids, the immense hollow regions between everything else. Together, these 4 components make up the skeleton of the cosmos, and the cosmic web is the name given to the whole. Understanding why the web looks the way it does, and mapping it in enough detail to extract its secrets, is the task that cosmologists have been working toward for the better part of a century. The fact that we have, in the last 18 months, achieved something genuinely unprecedented in that mission, photographing an individual filament, tracing 164,000 galaxies back to within 1 billion years of the Big Bang and identifying the single largest structure ever found, is the subject of this documentary. But first, we need to understand why it took this long. Why was something this enormous, this fundamental, so extraordinarily difficult to see? The universe is 13.787 billion years old. Modern cosmology, as a serious quantitative science, is roughly 100 years old. The cosmic web was theoretically predicted for the first time in the early 1970s. The first hard observational evidence for its existence emerged only in 1986, and the first direct high-definition photograph of a single cosmic filament, one individual strand of the web, was published on the 29th of January 2025. That timeline deserves to be read twice because it tells you something important. The cosmic web is not merely large. It is the most difficult thing to see that has ever existed. The problem is not distance, though distance is certainly a factor. The problem is brightness, or rather the almost total absence of it. The filaments of the cosmic web are not primarily made of stars. They are made of gas and dark matter. The dark matter is, by definition, undetectable by any telescope currently in operation. It emits no light, absorbs no light, and deflects light only gravitationally through lensing effects that require exquisite precision to measure. The gas is a different challenge. Hydrogen, the most abundant element in the universe, does emit light, but at such feeble intensity that for most of the 20th century, the instruments capable of detecting it simply did not exist. The light from a cosmic filament, having travelled for billions of years across expanding space, arrives at Earth so attenuated that it registers as a whisper inside a hurricane. Everything around it, galaxies, quasars, active galactic nuclei, screams at vastly higher volumes, and the whisper is lost. This is the filament visibility problem, and it has haunted observational cosmology for nearly 50 years. Theorists have known the web is there. Simulations have reproduced it with stunning fidelity. The computational model, known as the Millennium Simulation, run at the Max Planck Institute for Astrophysics in Garching, Germany, in 2005, reproduced the large-scale structure of the universe with a resolution so sharp that when the simulated web was compared to the observed distribution of galaxies, the match was, in the words of one reviewer, disquieting in its precision. Disquieting because the simulation told cosmologists what they should expect to see, but the real universe stubbornly refused to glow brightly enough to confirm it in the detail required. So for decades, cosmologists mapped the web indirectly. They mapped the galaxies, not the gas. They assumed, correctly as it turned out, that galaxies are biased tracers of the underlying dark matter web, meaning that where the simulation said a filament should exist, a string of galaxies would be found. This method produced the first real maps of the large-scale structure. The earliest was the CFA Redshift Survey, led by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, which published what came to be known as the Slice of the Universe in 1986, a wedge-shaped map of 1,099 galaxies that, for the first time, showed the filamentary, bubble-like structure of cosmic matter distribution to anyone with eyes to see it. Valérie de Laparent was a graduate student who took one look at the preliminary map, turned to her supervisor Geller, and said words that have since become legendary in cosmological circles. "It looks like a bubble bath." That paper stopped physicists mid-sentence. The universe was not a random distribution of points. It was structured, it was organised. And the organisation was visible, staring back from a hand-drawn diagram on a page of the Astrophysical Journal Letters in 1986 to anyone who chose to look. But those early maps had a fundamental limitation. They showed galaxies, not the web itself. They showed the bright knots at the filament intersections, not the threads between them. And the threads, it turned out, were where almost all the unresolved physics lived. Because the cosmic web is not merely a backdrop for galaxies to sit against. It is the delivery mechanism for the gas that feeds those galaxies. It is the pipeline through which hydrogen flows from the voids into the filaments, and from the filaments into the forming galaxy at the node. and from there into the engine rooms of stars. Map the web at sufficient resolution, and you understand how galaxies are fed. Understand how galaxies are fed, and you understand why some galaxies form stars furiously, and others die quiet, stellar formation deaths in middle age. Everything connects, and none of it is accessible until you can see the filaments directly. Which brings us to the second, deeper problem. Because even if you build a telescope sensitive enough to detect the faint hydrogen glow of a cosmic filament, you face a more insidious obstacle. One that took cosmologists years to fully articulate, and whose implications are still being worked through today. It is called the missing baryon problem, and it may be the single most embarrassing gap in our understanding of the visible universe. Here is the situation. The Big Bang model predicts, with extraordinary precision, how much ordinary matter, protons, neutrons, electrons, the stuff of atoms, was produced in the first few minutes of the universe's existence. The prediction is not vague. It is backed by the ratios of light elements observed in the oldest stars, by the temperature fluctuations in the cosmic microwave background, by multiple independent lines of evidence that all converge on the same number. Ordinary matter, the kind you and I are made of, should account for roughly 4.9% of the total energy content of the universe. Dark matter adds another 26.8%. Dark energy provides the remaining 68.3%. These are not round numbers. They are the product of decades of measurement, and they are as solid as anything in physics. The embarrassing part is this. When you go looking for all that ordinary matter, when you count up the atoms in all the observed galaxies, in all the observed galaxy clusters, in all the observable hot gas detected by X-ray telescopes, you find only about half of what the Big Bang says should be there. Roughly 40 to 50% of all ordinary matter in the universe is missing, not dark matter, not some exotic beyond the standard model particle. Plain, ordinary, garden variety baryonic matter, the matter we fully understand, is missing. This is not a small discrepancy. Half of everything is not a rounding error. For a while, it was one of the most uncomfortable open questions in cosmology. Where are the other half of all the atoms? The leading hypothesis, developed over the course of the 1990s and refined through the 2000s, pointed squarely at the cosmic web filaments. The missing baryons, theorists argued, are hiding in the gas threads between galaxies, in a phase known as the warm-hot intergalactic medium, the WIM. This is gas heated to temperatures between 100,000 and 10,000 Kelvin by gravitational compression as it falls along filaments. Hot enough that it does not form stars, cool enough that it does not emit the bright X-ray signatures detectable with older telescopes. It sits in a temperature range where it is essentially invisible to every instrument that preceded the current generation. The WIM hypothesis said, in effect, the missing baryons are not missing. They are in the filaments. We just cannot see them yet. Three questions have therefore haunted observational cosmology for the better part of 3 decades, running simultaneously and feeding one another in ways that make the whole problem both more complex and more urgent. First, where exactly are the missing baryons, and are they really in the WIM? Second, what is the dark matter that forms the skeletal scaffold of every filament, and why, after a century of searching, have we never once detected it directly? Third, how do the filaments actually feed the galaxies? What is the physics of gas flow from the cosmic web into a forming galaxy? None of these 3 questions had a clean answer as recently as 5 years ago. All 3 have moved significantly, though not all the way, in the last 18 months. And to understand how they moved, you need to first understand exactly how hard it was to get here. The story of the cosmic web is, at its core, a story about the limits of human instruments and the stubbornness of human curiosity. For most of the 20th century, astronomers were essentially archaeologists working in the dark, building a picture of the universe's structure from the faintest traces it left behind. Not because the universe was hiding from them deliberately, but because the light it produced was genuinely, physically, almost impossibly faint. Let's go back to the beginning. Not the beginning of the universe, but the beginning of the idea. In 1933, a Swiss-American astronomer at the California Institute of Technology named Fritz Zwicky was studying the Coma Cluster, a dense collection of galaxies roughly 330 million light-years from Earth, when he noticed something that should not have been possible. The galaxies in the cluster were moving far too fast, based on the visible mass of the cluster, the mass you could estimate from counting up the light from all its member galaxies. The gravitational force available was nowhere near strong enough to hold the cluster together. The individual galaxies should have been flying apart long ago. They were moving at velocities that would have dispersed the cluster within a fraction of the universe's lifetime. And yet the cluster was manifestly not dispersing. It was stable, dense, and gravitationally bound. Zwicky concluded that there had to be additional, invisible mass holding it together. He called it, in his characteristically direct German Dunkel Materie, dark matter. And then, almost universally, the astronomical community declined to take him seriously. Zwicky was famously abrasive, prone to spectacular feuds with colleagues, and widely regarded as a difficult person. His dark matter hypothesis was shelved. It would wait 40 years for someone with sufficient patience, precision, and political skill to resurrect it. That person was Vera Rubin, and the year was 1970. Rubin, working at the Carnegie Institution of Washington, alongside instrument specialist Kent Ford, had developed a new approach to measuring galaxy rotation curves, the velocity at which different parts of a spiral galaxy orbit its centre. By measuring the Doppler shift of light from hydrogen gas across the face of the Andromeda galaxy, Rubin and Ford produced a result that should have been a curve, fast at the centre, falling off toward the edges as Newton's laws demanded for a mass concentrated at the galactic core. Instead, the rotation curve was flat. Stars at the edge of the galaxy were orbiting at essentially the same speed as stars near the centre. The only explanation was that the galaxy was embedded in a vast invisible halo of mass extending far beyond its visible boundary. Dark matter, again, only this time presented with such precision and reproducibility that the community could not dismiss it. Vera Rubin went on to measure the rotation curves of 60 additional galaxies over the following decade, finding the same result in every single one. Dark matter was not a quirk of one cluster or one galaxy. It was universal, and if it was universal, it had to have a structure, a distribution. And that distribution, cosmologists began to realise in the early 1970s, was not smooth. It was filamentary. The theoretical framework for understanding why came primarily from the Soviet school of cosmology, and in particular from a remarkable physicist named Yakov Borisovich Zeldovich. Zeldovich was, by any measure, one of the most productive scientists of the 20th century, a man who had contributed to the Soviet atomic bomb program, to the theory of nuclear chain reactions, to stellar physics, to the theory of black holes, and who then pivoted in middle age to cosmology and proceeded to redefine it. In 1970, he published what became known as the Zeldovich approximation, a mathematical framework for describing how small density fluctuations in the early universe, the tiny ripples encoded in the cosmic microwave background, would evolve under gravity into the large-scale structure we observe today. The Zeldovich approximation predicted something specific and surprising. The first large structures to collapse under their own gravity would not be spherical. They would be flat. They would form thin sheets of matter, pancakes, Zeldovich called them, and then those pancakes would fragment and fold into the filamentary network that, he argued, would constitute the skeleton of the universe on the largest scales. He was, in the broad strokes, correct. The cosmic web looks like the evolved product of those pancakes, and this is one of the things I find most remarkable about the whole history of this subject. That a Soviet physicist in 1970, working with pencil, paper, and the mathematical machinery of fluid dynamics, could predict with qualitative accuracy the structure of the entire observable universe, before a single filament had been observed. But qualitative accuracy is not enough. Physics requires quantitative confirmation. For that, you needed maps. The CFA survey of 1986 was the first, and it was transformative. But its resolution was limited. The galaxies mapped were all within roughly 200 million light-years, a bubble barely 5% of the radius of the observable universe. It showed the local web, but could not reach back in time to watch the web forming. It confirmed the web's existence, but could not constrain the physics driving it. Subsequent surveys pushed further. The 2-degree field galaxy redshift survey in the early 2000s mapped 245,591 galaxy redshifts across a larger volume. The Sloan Digital Sky survey, beginning in 2000, and eventually cataloguing more than 3 million galaxies and quasars, produced the most detailed 3-dimensional map of the local universe in history. Every new generation of survey pushed the map deeper, sharper, and further back in time, but every galaxy survey, however magnificent, suffered from the same fundamental limitation. It was mapping the galaxies, not the web. The galaxies are the bright beads on the string, not the string itself. And the physics of what happens in the filaments between the beads, the gas dynamics, the temperature structure, the flow rates, the interaction of baryonic matter with the dark matter scaffold, remained almost entirely beyond the reach of observation. There were indirect methods. Quasar absorption spectra, in which the light from distant quasars passed through intergalactic gas and left characteristic spectral fingerprints, gave hints about the gas's composition and temperature. The Sunyaev-Zeldovich effect, in which the cosmic microwave background is distorted as it passes through hot gas in galaxy clusters, offered limited glimpses of the thermal state of gas in the densest nodes of the web. None of these methods could produce an image. None of them could show you the filament directly. Its shape, its extent, its density profile, its relationship to the galaxies it fed. For that, you needed to detect the hydrogen emission directly. And for that, you needed an instrument that did not yet exist. 3 technological developments, converging across the first 2 decades of the 21st century, changed that calculus. The first was the commissioning of MUSE, the multi-unit spectroscopic explorer, on the European Southern Observatory's Very Large Telescope at Paranal, Chile, in 2014. MUSE is an instrument of extraordinary ambition, a spectrograph that divides its 1 arc-minute field of view into 24 subfields, each feeding a separate spectrograph, allowing it to simultaneously capture both the spatial and spectral properties of everything it sees. In practical terms, it means that a single MUSE observation produces a 3-dimensional data cube, 2 spatial dimensions and 1 wavelength dimension, for every photon collected. It is not merely a camera, it is a machine for understanding the composition, velocity, and temperature of everything the VLT can see. The second development was a revolution in detector sensitivity. The charge-coupled devices at the heart of modern astronomical cameras had by the mid-2010s reached efficiencies close to the theoretical maximum, converting more than 90% of incoming photons into measurable signals, compared to less than 30% for the photographic lake plates used in earlier surveys. This sounds modest but is transformative. It means that observations that would have required 3 times as much telescope time in the 1990s can be completed in 1. And telescope time is the rarest commodity in all of observational science. The third development was the launch, on the 25th of December 2021, of the James Webb Space Telescope. This is not the place to rehearse the extraordinary story of JWST's construction, its 25 years of delays, its $10 billion price tag, or the 344 specific engineering deployments that had to succeed perfectly in sequence for the telescope to reach operational status. That story has been told elsewhere, and it deserves its own documentary. What matters here is what JWST offers to the study of the cosmic web. A mirror 6.5 meters in diameter, infrared sensitivity extending to 28 micrometers wavelength, and a resolution so sharp that what Hubble showed as a single smear now resolves into dozens of distinct structures. For the cosmic web specifically, JWST's ability to detect faint, high redshift galaxies with extreme precision meant that for the first time, astronomers could place individual galaxies into their correct positions across 13 billion years of cosmic history with enough accuracy to actually see the filamentary structure in which those galaxies are embedded. These three tools, MUSE on the ground, Webb in space, and a new generation of computational pipelines capable of extracting structure from datasets of previously inconceivable size, were converging on the same problem from different angles, and the results, when they came, were not incremental. They were transformative. But before we get to those results, there is one more layer of complication to add, because it was not merely the filaments that were proving difficult to see. It was also the question of how large the Webb's structures could actually grow, and the answer to that question, when it arrived in February 2025 from a team working not with MUSE or JWST, but with a 30-year archive of X-ray satellite data, was genuinely shocking. The cosmological principle is one of the foundational assumptions of modern physics. It states, in its simplest form, that the universe looks the same from any point within it, that there is no preferred direction, no special location, no scale at which the universe stops being statistically homogeneous and isotropic. It is the assumption on which every cosmological model is built. Without it, you cannot derive Friedmann equations. Without it, you cannot interpret the Hubble constant. Without it, the entire edifice of modern cosmology becomes, if not wrong, then radically incomplete. The cosmological principle works perfectly well below a certain scale, up to roughly 300 megaparsecs, a billion light-years. The universe is, on average, statistically smooth. Structures exist, but they average out. No single cluster or supercluster dominates the mass distribution so thoroughly that the principle breaks down. The question is, what happens above 300 megaparsecs? Does the universe stay smooth, or do structures exist at scales that challenge, or even break, the cosmological principle? In 2013, a structure was reported in the distribution of gamma-ray bursts that, if real, would have been the most dangerous challenge to the cosmological principle ever identified. It was called the Hercules Corona Borealis Great Wall, and the estimate of its extent was not merely large. It was estimated to span approximately 10 billion light-years, nearly 1/10 of the entire observable universe's diameter. If confirmed, it would be so large that it would take light itself, travelling for 10 billion years, to cross from one side to the other. That is not a structure, that is a feature of the universe's geometry, and a structure on that scale would violate the cosmological principle so severely that it would require not an adjustment to our models, but a wholesale reconstruction. The Hercules Corona Borealis Great Wall remains controversial. The data on which it rests, gamma-ray burst positions whose distances are notoriously difficult to measure precisely, is not universally accepted. Some cosmologists regard it as a statistical artifact. Others take it seriously. The debate has not been resolved, but then, in February 2025, a team led by Hans Boehringer at the Max Planck Institute for Extraterrestrial Physics, working with galaxy cluster positions measured in X-rays by the Rosat satellite over the previous 3 decades, announced the discovery of Quipu, and the debate became considerably more urgent. There is something almost poetic about the name. Quipus were the record-keeping tools of the Inca Empire, lengths of knotted cord whose knots encoded information about taxation, census data, agricultural yields, calendars, and histories in a numerical system that Spanish conquistadors, lacking the cultural context to decode it, largely destroyed. Thousands of quipus survive in museums and archives worldwide, their records largely unread because the decoding tradition was severed. They are repositories of information that we know exist but cannot yet fully interpret. Hans Boehringer saw one in a museum near Santiago, Chile, while working at the European Southern Observatory, and when the structure his team had found resolved on his computer screen, a long central axis with smaller filaments branching off to the sides, like knots on a cord, the name came immediately. Quipu, the cosmic structure, is 1.3 billion light-years long. That number deserves to sit alone on the page for a moment before we add context to it, because context, in this case, simultaneously helps and fails. 1.3 billion light-years. The entire Milky Way galaxy is approximately 105,700 light-years in diameter. Quipu is 12,300 Milky Ways long. The distance from here to the Andromeda galaxy, the nearest large galaxy, which astronomers discuss with a casual familiarity that belies the extraordinary number, is 2.537 million light-years. Quipu is 512 times longer than that distance. The Laniakea supercluster, which contains the Milky Way, the Local Group, the Virgo cluster, and hundreds of other galaxy clusters within a volume that seemed unimaginably large when it was first described in 2014, spans 520 million light-years. Quipu is 2.5 times larger than Laniakea. The mass enclosed within Quipu is approximately 2 times 1017 solar masses, 200 quadrillion solar masses, or 200,000 times the mass of the Milky Way. It contains within its extended form roughly 45% of all galaxy clusters and 30% of all galaxies within the survey region. It is not a structure sitting inside the universe. It is a structure that contains a significant fraction of the observable universe's visible matter within a single coherent object. Beringer and his team found Quipu using data from the Ross et al. Sky survey, the only complete X-ray map of the entire sky, conducted between 1990 and 1999. X-ray galaxy clusters, clusters of galaxies whose intracluster gas has been heated to tens of millions of Kelvin and glows brightly in X-rays, are ideal tracers of the underlying dark matter web because they mark the densest nodes where multiple filaments intersect. By cataloguing X-ray clusters across the survey volume and mapping their three-dimensional distribution using their measured redshifts, the Class IX survey team built a picture of the large-scale structure between 130 and 250 megaparsecs from Earth, and within that volume, 5 enormous superstructures emerged. Quipu was the largest. The others, named Shapley, Serpens Corona Borealis, Hercules and Sculptor Pegasus, were themselves enormous, but Quipu dwarfed them, and taken together the 5 superstructures contained an almost bewildering fraction of the local universe's mass. Their combined volume fraction was 13% of the survey volume. Their combined galaxy cluster fraction was 45%. If you randomly placed yourself somewhere in the survey volume, you would have a nearly 1 in 8 chance of landing inside one of these structures. The immediate question, posed in the paper's abstract, and echoed in every press release that followed, was whether structures of this scale were consistent with the cosmological principle. The Beringer team's answer was carefully hedged. Yes, barely, within the uncertainties. The Lambda CDM model, the standard model of Big Bang cosmology, incorporating dark matter and dark energy, does produce superstructures with properties similar to Quipu in its simulations. The structures are unusual but not forbidden. They sit at the high end of what the model allows, but they do not, strictly speaking, break it. But barely consistent within the uncertainties is not the same as comfortably predicted. It is the kind of answer that keeps theorists awake at night, because every time an observation pushes against the edge of what a model allows, without yet breaking it, the model is telling you something. It is telling you that it is running out of margin. And models that run out of margin tend, historically, to be models that are eventually replaced. I want to be precise about what I mean here, because this is a point where the popular science coverage has sometimes muddied the waters. Quipu does not prove that the cosmological principle is wrong. It does not single-handedly overturn Lambda CDM. What it does is add weight to a growing pile of observations. The Hercules Corona Borealis Great Wall, the South Pole Void, various anomalies in the Hubble constant measurements, and now Quipu, that collectively suggest our models may be optimized for a universe that is slightly more homogeneous than the one we actually live in. The gap between the model and the data is not yet definitive, but it is widening, and the direction in which it is widening points consistently toward the possibility that structure, on scales larger than we assumed were important, matters more than our current models account for. There is also a practical consequence, one that Beringer's team emphasized emphatically. These superstructures are not merely theoretical curiosities. They affect real, measurable cosmological quantities. The most famous of these is the Hubble constant, the number describing how fast the universe is expanding, which has been at the centre of one of the most contentious debates in modern cosmology for the past decade. The so-called Hubble tension is a discrepancy between the value of the Hubble constant measured from the cosmic microwave background, which gives approximately 67, 4 kilometers per second per megaparsec, and the value measured from distance ladders built on nearby galaxies and Cepheid variable stars, which consistently comes out around 73 kilometers per second per megaparsec. The two methods disagree by roughly 9%, using data precise enough that the disagreement cannot be explained by measurement error alone. Various solutions have been proposed: new physics beyond the standard model, a modification of dark energy, a revision of the CMB analysis. But Boehringer's team pointed to a more prosaic possibility, one that does not require new physics at all, if you live inside or near a large superstructure, and we do. The Milky Way sits within the Laniakea supercluster, which borders on the regions mapped in the Classic survey. Then the peculiar velocities of galaxies around you, driven by the gravitational influence of that superstructure, will systematically bias your local measurements of the Hubble constant. The superstructure creates a local flow of matter that, if uncorrected for, would produce exactly the kind of discrepancy observed. The Hubble tension might not be new physics. It might be the gravitational fingerprint of Quipu. That is not a small claim. It is potentially one of the most significant findings about the Hubble tension in years, and it sits there quietly inside a paper about a structure whose name most people do not yet know. But Quipu was not the only major development of early 2025. On the same day that ESO published Boehringer's results, the 29th of January 2025, a second team, thousands of kilometers away in the mountains of Chile, released an image, not a data table, not a redshift catalogue, an actual direct photographic image of a cosmic filament, the first of its kind in history. And the person most responsible for it was a PhD student who had spent the better part of his program staring at an almost entirely blank patch of sky. Davide Tornotti is not a famous name. He was not famous on the 29th of January 2025, when the European Southern Observatory published his image and the paper it accompanied, even though that image represented something unprecedented in the observational history of the universe. He was a PhD student at the University of Milano Bicocca in Italy, in his late 20s, still accumulating the specific kind of patience and obsessive focus that PhD research either develops or breaks. He was not chasing a previously unknown phenomenon. He was not working on a moonshot project conceived by a tenured professor. He had chosen, deliberately and with full awareness of the difficulty, to spend the central chapter of his PhD trying to do something that several senior astronomers had privately doubted was achievable with current technology: directly photograph a cosmic filament. The choice of target had been made carefully. Not all cosmic filaments are equally photogenic, which is, admittedly, a strange sentence to write about objects that are almost entirely invisible, but some regions of the sky have been observed so extensively, and the astrophysical context around them mapped so thoroughly, that they offer the best hope of detecting a filament signal above the noise. The region Tornotti's team chose sits in the constellation of Grus, the Crane, in the southern hemisphere sky, at a right ascension of 21 hours, 42 minutes and 25.54 seconds, and a declination of -44 degrees 19 minutes 48.2 seconds. It contains two galaxies that each host an active supermassive black hole, what astronomers call active galactic nuclei, or AGN. These AGN were already known and already catalogued. What the team hypothesized, based on simulations of the cosmic web at similar epochs, was that two AGN at this redshift and spatial separation should be connected by a filament of intergalactic gas, fed along the dark matter scaffold between them. The hypothesis was sound. The physics was well understood. The prediction was specific and testable. The problem was the signal hydrogen gas in an intergalactic filament at the redshift of these two galaxies, which places them roughly 11 billion light-years away, meaning we are seeing them as they existed when the universe was only about 2 billion years old. Emits light through a process called Lyman alpha emission. A hydrogen atom in its lowest excited state releases a single photon as its electron falls back to the ground state, and that photon has a wavelength in the ultraviolet range. Stretched by 11 billion years of cosmic expansion, the ultraviolet photon arrives at Earth in the green part of the visible spectrum at approximately 513 nanometers. MUSE, the spectrograph on ESO's Very Large Telescope at Paranal, is exquisitely sensitive in exactly this wavelength range. It was, in a very real sense, designed for this kind of observation, but designed for it and capable of it are not the same thing. The Lyman alpha emission from an intergalactic filament is not merely faint, it is almost immeasurably faint. Consider what you are trying to detect. Hydrogen gas spread across a volume 3 million light-years in length and roughly a few 100,000 light-years in depth, glowing with a surface brightness so low that it is approximately 0 times fainter than the darkest patch of night sky visible to the naked eye. The sky itself, the glow of Earth's atmosphere, the scattered light of distant galaxies, the thermal noise in the detector, produces a background signal orders of magnitude brighter than what you are looking for. Extracting the filament from that background is not merely a technical challenge. It is, at some level, a philosophical challenge, an act of faith that the signal exists at all, sustained across months of observation, analysis and iteration. Tornotti began accumulating observations in 2022. The VLT had allocated the team observing time in blocks, nights here, nights there, spread across a schedule that accommodates hundreds of different research programs, competing for the most oversubscribed telescope in the Southern Hemisphere. Each block of observations was combined with the previous ones. Each new dataset had to be processed, calibrated, sky-subtracted, and integrated into the growing total. The noise floor dropped, glacially, hour by hour, as more photons were accumulated. Below the noise, the team knew, or believed, the filament was there. The simulation predicted it. The physics demanded it. But the data did not yet show it. 150 hours of total observing time. That is 6¼ days of pure telescope time, spread across multiple observing runs over roughly 2 years, all pointed at a single patch of sky just under 2 arc minutes across. A region so small that it would be comfortably covered by the period at the end of this sentence held at arm's length. 150 hours to capture light that had been travelling for 11 billion years. When the combined data finally reached sufficient depth to see the signal above the noise, the image that emerged was quiet at first, a faint, diffuse glow in the Lyman alpha channel, elongated across the field, connecting 2 brighter point-like nuclei. Tornotti and his collaborators ran their sky subtraction routines again. They checked for instrumental artifacts. They compared the signal to simulations. The signal was real. The filament was there. They ran additional spectral checks, measuring the velocity structure of the gas along the filament to confirm it was not merely a projection effect. 2 unrelated gas clouds that happened to lie along the same line of sight. The spectral measurements confirmed coherent gas structure across the full 3 million light-year extent. Not a coincidence, not an artifact. A real physical thread of intergalactic gas, connecting 2 forming galaxies, carrying the hydrogen that would eventually fuel the formation of new stars. The paper was submitted to Nature Astronomy. It was accepted after peer review. On the 29th of January 2025, the European Southern Observatory published an image showing the filament in purple against a Hubble Space Telescope background. An 11 billion year old whisper of light, finally made legible after 150 hours of patient listening. The significance was threefold. First, the discovery demonstrated that direct observation of cosmic filaments is achievable with current technology, opening the door to a systematic survey of filamentary structures across different redshifts and environments. Second, The morphology of the observed filament, its shape, extent, and density profile matched the predictions of the Illustris TNG simulation with what Tornotti described as substantial agreement, providing what cosmologists call a stringent test of the model. The model, in this case, passed. Third, and perhaps most importantly, the team was able, for the first time through direct measurement rather than inference, to trace the boundary between the gas residing inside the galaxies and the gas residing in the filament, the boundary between the fuel supply and the engine it was feeding. That boundary has enormous consequences for galaxy evolution models. The question of how galaxies receive their gas, whether it flows in cold and smooth along filaments or arrives hot and turbulent, having been shock heated at the virial boundary of the galaxy's dark matter halo, is one of the central unresolved debates of galaxy formation theory. Different modes of gas accretion predict different star formation histories, different galaxy morphologies, different metallicity profiles. With direct filament observations, you can begin to measure the gas properties on the filament side of the boundary, not just the galaxy side. You can, for the first time, see the pipe, not just the water coming out of the tap. Fabrizio Arrigoni Battaglia, the Max Planck Institute staff scientist who co-supervised the work, gave the best summary of where this leaves us. He quoted a Bavarian saying, "Eine ist keine, one doesn't count. One observation, however beautiful and unprecedented, is not yet a statistical sample, it is a proof of concept, a demonstration. The real science begins when you have dozens of these images, spread across cosmic time, covering multiple redshift ranges, mapping the diversity of filament properties across different cosmic environments. That work has already begun. Tornotti's team filed for additional Muse observing time immediately after the paper's publication. Other groups, inspired by the result, were doing the same. And in the background, a larger, more ambitious instrument was preparing to contribute data that would change the entire scale of the question. What I find genuinely moving about Tornotti's story is not the discovery itself, though the discovery is extraordinary. It is the particular quality of the commitment required to make it. 2 years of intermittent observations, 150 hours pointed at what looked, to any casual observer, like an empty patch of sky. The patience to accumulate signals so faint that it barely registers as a signal at all, trusting in the physics and the simulations and the mathematics enough to keep going even when the data showed nothing but noise. Science, at its most demanding, asks for exactly that quality. Not genius, not inspiration, patience, precision, and the willingness to keep listening even when the universe is not yet ready to answer. And the universe answered, but Tornotti's image, as unprecedented as it was, told us about a single filament, a single thread in a structure that contains billions of such threads. To understand the web as a whole, to trace its full extent across cosmic history, to map how it formed and how it evolved, and how the galaxies within it grew under its influence, you needed not 150 hours on one small patch of sky, but a survey of a size and depth that had never been attempted before. That survey was already complete. Its results were published on the 11th of May 2026. And they rewrote, in a single paper, what we thought we knew about the first billion years of the universe's large-scale structure. The name of the survey is Cosmos Web. The acronym reflects its lineage. Cosmos stands for Cosmic Evolution Survey, a project that has been accumulating data about a single carefully chosen patch of sky for more than 2 decades, building a multi-wavelength archive of extraordinary depth and breadth. The web portion refers to its primary scientific objective: to map the cosmic web across cosmic time using the capabilities of the James Webb Space Telescope. It is the largest general observer program selected for Webb in its first operational cycle, consuming 255 hours of the telescope's time, and the patch of sky it covers, a contiguous area roughly equal in extent to 3 full moons, sounds modest until you consider what Webb sees when it looks at it. The choice of the Cosmos field was not arbitrary. Over the preceding 20 years, the Cosmos field had been observed by essentially every major telescope and space observatory in operation. Hubble, Spitzer, Chandra, XMM Newton, the Very Large Array, Subaru, the Canada-France-Hawaii telescope, and dozens of others. The result was a dataset of almost unparalleled richness, a complete multi-wavelength census of every galaxy visible in that patch of sky, from radio waves through X-rays, with photometric redshift estimates for hundreds of thousands of objects. This existing dataset was the foundation on which Cosmos Webb was built. Webb did not enter an unknown field. It entered the most studied 6 square degrees of sky in the history of observational astronomy, and looked at it with eyes that made everything that had come before look blurry. The specific JWST capabilities that Cosmos Webb exploited were the ANIACAM instrument's ability to simultaneously image in 4 infrared filters, spanning wavelengths from 1.15 to 44 micrometers, and the NIRIS instrument's capacity to perform slitless spectroscopy across a portion of the field. Together, these instruments gave the survey team 2 things that previous generations of cosmic web maps had lacked: the ability to detect very faint, very high redshift galaxies that Hubble could not see, and the ability to measure the redshifts of those galaxies with unprecedented precision. Redshift precision matters enormously for cosmic web mapping, because the web is a 3-dimensional structure. A galaxy survey sees galaxies projected onto a 2-dimensional sheet of sky, and it is only by measuring each galaxy's redshift, which gives its distance, and therefore its position along the line of sight, that you can recover the 3-dimensional distribution. The precision of your redshift measurement determines the resolution of your 3-dimensional map along the line of sight direction. A poorly measured redshift smears a galaxy across a thick slice of cosmic time, while a precisely measured one pins it to a specific epoch with much lower uncertainty. Hubble error measurements of the cosmos field achieved photometric redshift uncertainties of roughly 0.03 in redshift units, sufficient to identify large structures but insufficient to resolve their internal organization. JWST achieves uncertainty closer to 0.01 for objects bright enough to make the catalogue, and for the faintest, most distant objects, the improvement is even more dramatic because JWST can detect them at all, whereas Hubble could not. This is not merely a factor of 3 improvement in precision, it is the difference between seeing a neighbourhood as a smear and seeing it as individual houses. The Cosmos Webb team, led by graduate student Hossein Hatamnia at the University of California, Riverside, under the supervision of distinguished Professor Bahram Mobasher, developed a new pipeline to translate the galaxy catalogue into a density field, a continuous map of matter over density, as a function of position and redshift, covering the range from the nearby universe back to a redshift of approximately 7, corresponding to when the universe was roughly 770 million years old. Their catalogue contained 164,000 galaxies. Their map was released publicly alongside the full pipeline code and a video showing the cosmic web evolving across 13 billion years. The comparison with the previous Hubble-era map of the same field was, in Mobasher's words, truly significant. What had previously appeared as a single broad overdense region in the Hubble map resolved, in the JWST map, into multiple distinct structures separated in redshift space with individual filaments and void boundaries that had been blurred together by the coarser resolution of the earlier data. Structures that astronomers had been treating as single objects turned out to be projections of multiple distinct structures lying at different distances along the same line of sight, artificially combined into a single apparent overdensity by the limited precision of Hubble's redshifts. This is not a minor calibration correction. This is a fundamental revision of what we thought the large-scale structure looked like in the early universe. If the previous maps were systematically overestimating the size and mass of individual structures, because they were blurring multiple structures together, then the statistics of cosmic structure formation that those maps informed were also systematically biased. Models of how fast the web grew, of what fraction of mass was in filaments versus voids versus clusters at different epochs, of how the galaxy population evolved in different large-scale environments. All of these could have been calibrated against a map that was substantially blurrier than the reality. The Cosmos Web Map is the first map precise enough to be a genuinely reliable calibration standard, but the most consequential result from Cosmos Web was not the map itself. It was what the map showed about the relationship between a galaxy's properties and its position within the cosmic web. For decades, theoretical models of galaxy evolution had predicted that environment mattered, that a galaxy forming at the dense node of multiple intersecting filaments should evolve differently from a galaxy forming in a less connected region, which should evolve differently from a galaxy forming in a void. The idea is intuitive. A galaxy at a node has access to gas flowing in along multiple filaments simultaneously, potentially fueling higher star formation rates. A galaxy in a void has only whatever gas was present locally when it first collapsed, and it evolves in near isolation. These environmental effects had been observed statistically in galaxy surveys going back to the Sloan Digital Sky Survey, but the statistical signal was always blurred by the imprecision of the large-scale structure maps. It was hard to say definitively whether a galaxy was truly at a node, or in a filament, or in a void, when the map itself was uncertain by tens of millions of light-years. Cosmos Web's precision map allowed the team to assign cosmic web environment labels, node, filament, sheet, void, to each of the 164 zero-known galaxies in the catalogue with much greater confidence than had ever been possible before. The results were clear. Galaxies in denser cosmic web environments, the nodes and filaments, had on average higher stellar masses, redder colours, and lower specific star formation rates than galaxies in voids at the same redshift. This is the so-called star formation quenching effect in action, and its correlation with large-scale cosmic web environment has now been traced back to redshift 7, within the first billion years of the universe. What this means is that the cosmic web was already influencing galaxy evolution as soon as it existed. The environment into which a galaxy was born, the particular filament intersection, the particular local density, determined by the dark matter distribution at the moment the galaxy collapsed, has shaped its entire subsequent history, its colour, its mass, its star formation rate, all the way from when the universe was less than 1 billion years old to the present day. This is the stakes-raising revelation of Cosmos Web. It is not merely that we have a better map. It is that the map proves, for the first time at these early epochs, that the cosmic web is not a passive backdrop against which galaxies evolve. The cosmic web is the primary driver of galaxy evolution. The skeleton is not inert. It is causally connected to every star ever formed, to every heavy element ever synthesized, to the chemical composition of every planet in every stellar system in every galaxy in the observable universe, including the carbon in your body, including the iron in your blood. That is a statement I want to sit with for a moment, because its implications go beyond astronomy. The pattern of the cosmic web, the specific distribution of dark matter density fluctuations that emerged from the inflationary period of the Big Bang, imprinted on the universe at a fraction of a second of age, amplified by gravity over billions of years into the filamentary architecture we are now mapping. That pattern determined, in a probabilistic but real sense, which regions of the universe would produce the chemical complexity necessary for life. The cosmic web is not merely the largest structure we know of, it is the structure that made chemistry possible at cosmic scales. It is the structure that made us possible. There is more still, because the 164,000 galaxy map of Cosmos Web and the first direct image of a cosmic filament by Tornotti's team and the discovery of Quipu by Boehringer's team, these three developments in an 18-month window are not the end of the story. They are the beginning of the era of precision cosmic web science. And precision, in science, always reveals complications that approximation conceals. The Cosmos Web Map, for all its resolution, covers only 0.6 square degrees of sky, a region that, in the grand architecture of the observable universe, is roughly analogous to a single city block in a planet-spanning metropolis. It gives unprecedented depth in that block, but it cannot, by itself, tell you whether that block is representative. The Quipu discovery tells you about a superstructure 130 to 250 megaparsecs away, the nearby universe by cosmic standards. The Tornoti filament tells you about a single structure at redshift 3.3 when the universe was 2 billion years old. None of these results, individually or together, constitute a complete map of the cosmic web. They constitute, rather, the first high-resolution measurements of specific regions and specific scales. They prove that the tools now exist to map the web at the required precision. They do not yet constitute a census, and there is something even more troubling beneath the surface of these results. Because the missing baryon problem, the uncomfortable fact that roughly half of all ordinary matter in the universe remains undetected, has not been solved by any of these discoveries. The Cosmos Web Map detects galaxies, not diffuse gas. Tornoti's image detected hydrogen gas in a single unusually bright filament between two AGN. The AGN were almost certainly illuminating the gas with ultraviolet radiation, and making it glow far more brightly than a typical filament would without such illumination. The warm-hot intergalactic medium, the phase of gas believed to contain the missing baryons, remains largely inaccessible to current instruments. This is the deepest, most persistent problem in cosmic web science. It is the problem from which the other problems derive their urgency. And it is the problem that two new observational approaches, one already delivering results and one currently being built, are specifically designed to address. But these complications, these unresolved tensions, lead us directly to the question of what the mapping of the cosmic web actually tells us about the deep physics of the universe. Because the pattern of the web is not merely beautiful, it is information, it is a signature it carries, encoded in the statistics of its filament lengths and void diameters and cluster masses. The imprint of the physical conditions that existed in the first second of the Big Bang. If you could measure the web with sufficient precision across a large enough volume, you would have a measurement of the universe's fundamental parameters, its matter content, its dark energy equation of state, the primordial amplitude of density fluctuations, that would either confirm our best models or shatter them. This is the ultimate ambition of cosmic web science, not just to map the architecture, but to read it, to decode, from the largest structure in existence, the physics of the very first moment. Every major discovery in the history of science has followed the same arc. The initial revelation, which seems to answer a question, gives way to a deeper understanding of the question, which reveals that the answer was incomplete. The cosmic web is following this arc with almost metronomic precision. The three major discoveries of 2025 and 2026, Quipu, the Tornoti filament, and the Cosmos Web Map, each answered something important, and each, in answering it, sharpened a set of more difficult questions that were already lurking. Let's begin with what the new discoveries actually confirm. The most basic confirmation is that the lambda CDM model, the standard model of cosmology that incorporates cold dark matter as the primary structural component of the universe, plus dark energy as a cosmological constant, is correct in its broad predictions about the cosmic web. Tornoti's filament, when compared to the Illustris TNG simulation's predictions for structures of similar mass and redshift, showed substantial agreement. The Cosmos Web Map's large-scale structure statistics are consistent with what lambda CDM simulations predict for those epochs and scales. The four additional superstructures found alongside Quipu, Shapley, Serpens Corona Borealis, Hercules and Sculptor Pegasus all have analogues in lambda CDM simulations. Even if they sit at the high end of the predicted distribution, this is genuinely reassuring. Lambda CDM is built on a scaffold of assumptions that are, individually, each enormously well tested but collectively require that a universe filled with particles and forces that we have never directly detected, dark matter, dark energy, evolves in ways consistent with everything we observe. The fact that the most detailed direct observations of the cosmic web, at multiple scales and epochs, continue to match the model's predictions is not a trivial result. It is a significant validation of a theoretical framework that has, periodically and despite its successes, been pronounced dead by those who find its assumptions too audacious. But the confirmations are inseparable from the complications, and the complications are serious. The first is the missing baryon problem, which the new discoveries have not solved, and in some ways have made more acute. The Cosmos Web Survey found 164,000 galaxies in its 0.6 square degree field. The galaxies are the bright islands in the web, but the gas in the filaments between them, the warm-hot intergalactic medium, is not in this catalogue. It is not in any catalogue. The WIM emits primarily in the soft X-ray and extreme ultraviolet bands at a surface brightness so low that only the planned Athena X-ray Observatory, the European Space Agency's next-generation flagship X-ray telescope, designed with detection of the WIM as one of its primary science goals, would have had the sensitivity to systematically survey it. Athena was descoped in 2023 due to cost constraints and renamed New Athena with a smaller aperture and reduced science capabilities. Whether New Athena retains sufficient sensitivity to resolve the missing baryon problem remains a subject of debate in the X-ray astronomy community. In the interim, a different approach has emerged as unexpectedly powerful. Fast radio bursts, FRBs, are millisecond flashes of radio emission of apparently extragalactic origin whose physical mechanism remains unidentified. Their discovery in 2007 and the subsequent realization that they occur at a rate of roughly 10,000 per day across the observable sky created a new observational tool whose significance is still being worked through. FRBs are powerful probes of the intergalactic medium because they are affected by the dispersion measure of the gas they pass through on their way to Earth. Dispersion measure is a measure of the column density of free electrons along the line of sight, and in an ionized gas like the YIM, dispersion measure and electron column density are directly related. A fast radio burst that has travelled through a cosmic filament will be more dispersed than one that has passed through an empty void. By cataloguing the dispersion measures of large numbers of FRBs with precisely localized host galaxies, you can, in principle, map the distribution of electrons along multiple lines of sight through the cosmic web, and from those electrons infer the distribution of baryons. The first statistical detection of the missing baryons using FRBs was achieved by a team led by Jean-Pierre Macquart in 2020, establishing what has since been called the Macquart relation, a correlation between FRB dispersion measure and host redshift that provided the first direct statistical evidence that the missing baryons are, indeed, in the intergalactic medium. More recent work, through 2025, has extended this approach to trace the actual distribution of those baryons along specific lines of sight. A 2025 study using the KIME and DSA-110 radio telescopes in North America correlated FRB dispersion measures with known large-scale structure along the simulcast lines of sight and found clear excess dispersion in directions where galaxy filaments are expected. Strong statistical evidence that the HIMV is concentrated in the cosmic web filaments as predicted. This is a significant result. It does not yet resolve the missing baryon problem in the sense of telling you the exact temperature, density and spatial distribution of the HIM in any specific filament, but it provides the clearest statistical confirmation to date that the missing baryons are where the theory said they would be. They are in the cosmic web. They are in the filaments. We still cannot see them directly, but we can now feel their gravitational shadow through the dispersion of radio waves, and the shadow has exactly the shape the model predicted. The second major complication, the one I find most personally unsettling, is the dark matter problem. This is not a new complication. It has been the central unresolved problem of fundamental physics for nearly a century since Zwicky's first dark matter hypothesis, but the new cosmic web observations make it more urgent in a specific and precise way. The cosmic web is, at its core, a dark matter structure. The dark matter scaffold forms first under gravity, collapsing from the small-scale density fluctuations of the early universe into the filamentary network. The baryonic gas, the ordinary matter, falls along the dark matter potential wells, flowing down filaments and collecting at nodes to form galaxies. This process is exquisitely reproduced by simulations like Illustris TNG, which model both the dark matter and the gas simultaneously and get the galaxy distribution, the filament statistics, and the large-scale structure right to a degree that, to me, is one of the most compelling validations of the dark matter hypothesis in existence. And yet we have never detected a dark matter particle. Not one. The leading candidates for decades were WIMPs, weakly interacting massive particles, predicted by supersymmetric extensions of the Standard Model to have masses in the range of 10 to 1,000 times the proton mass, and to interact with ordinary matter via the weak nuclear force, at a rate that, in the 1990s, seemed detectable with instruments of reasonable scale, detectors buried deep underground, in abandoned mines and purpose-built caverns, shielded from cosmic ray background, filled with xenon or germanium or other heavy nuclei, and sensitive to the tiny energy deposits that a WIMP interaction would produce, were built and operated and refined over 3 decades. The Lux detector, Xenon 1T, Panda Zeppelin, each new generation was larger, cleaner, and more sensitive than the last. Each new generation failed to find a signal, not a marginal signal, not an ambiguous candidate, null, nothing. Silence all the way down the Lux Zeppelin experiment, reporting its first results in 2022, achieved a sensitivity that placed the most stringent limits ever obtained on the WIMP nucleon cross-section, ruling out WIMP masses between roughly 10 and 40, 0 times the proton mass, at interaction cross-sections, down to approximately 10⁻47 square centimeters. That is, to put it concretely, roughly 100 times more sensitive than any previous detector, probing cross-sections so small that they correspond to an interaction probability that would require a WIMP to travel through a light year of solid lead before registering a single collision with a nucleus. And still nothing. I will be honest about what this means, because I think the science communication around dark matter detection limits has been somewhat coy about the implications. The WIMP hypothesis is not dead. There are still viable parameter space regions that even Lux Zeppelin has not yet reached. But the WIMP hypothesis has been progressively cornered into parameter spaces that a decade ago theorists would have described as unlikely. Every null result from every direct detection experiment narrows the range of viable WIMP models. Every null result at the Large Hadron Collider, which has searched for WIMP production directly in particle collisions, narrows it further. We are not yet at the point where the WIMP hypothesis is definitively excluded, but we are at the point where the confidence in WIMPs that pervaded particle physics in the 1990s has been replaced by a growing, uncomfortable uncertainty. Alternative dark matter candidates have proliferated in response. Axions, very light pseudoscalar particles originally proposed to solve the strong CP problem in QCD, are now among the most actively pursued dark matter candidates. Sterile neutrinos, primordial black holes, dark photons, fuzzy dark matter. The theoretical landscape has diversified dramatically as the WIMP exclusion limits have tightened. Each of these candidates would produce a slightly different cosmic web. Axion dark matter, for instance, would produce a web with slightly smoother filaments and slightly shallower void density profiles than WIMP dark matter, due to its quantum wave-like behaviour on small scales. If the Cosmos web map and future surveys, like the Euclid Space Telescope's dark matter map, achieve sufficient precision, they may eventually be able to discriminate between dark matter models not through direct detection, but through the statistics of the large-scale structure, using the shape of the web as a fingerprint for the physics of the dark sector. This is, to my mind, one of the most profound conceptual developments in contemporary cosmology. The possibility that the structure of the cosmic web might become a particle physics laboratory, that by measuring the statistics of filament widths and void sizes with sufficient precision, we might be able to constrain the mass and interaction properties of dark matter particles without ever detecting them directly, The web is not merely an astronomical object. It might be the most sensitive dark matter detector ever constructed by the universe itself over 13 billion years, and now finally readable with the instruments we have built. The third major complication is what might be called the homogeneity crisis. This is the growing tension between the cosmological principle and the observations of increasingly large structures. It is not yet a crisis in the scientific sense, a definitive falsification, but it has the character of a gathering storm. Quipu sits at 400 megaparsecs. The Hercules Corona Borealis Great Wall, if real, sits at 300 megaparsecs. Other anomalies at intermediate scales, the alignment of large-scale structure along specific directions, the so-called axis of evil in the CMB power spectrum that appears to prefer the ecliptic plane, various bulk flow measurements that suggest coherent motion on scales larger than lambda CDM predicts, have been accumulating for years. None of them individually is definitively inconsistent with the standard model. Together, they paint a picture of a universe that is slightly less homogeneous, slightly more directionally structured than our baseline assumption allows. The precise measurement of this tension is the central cosmological challenge of the coming decade. The Euclid Space Telescope, launched in July 2023, is in the process of mapping the three-dimensional positions of roughly 5 billion galaxies across 15,000 square degrees of sky, covering 1/3 of the entire celestial sphere, to redshifts up to approximately 2. This is a survey that will, when complete, dwarf every previous large-scale structure dataset by multiple orders of magnitude. The statistical precision it will achieve on the power spectrum of density fluctuations, on the baryon acoustic oscillation scale, and on the growth rate of structure will be sufficient to either confirm the cosmological principle at scales up to 1000 megaparsecs, or to detect deviations from it at a significance level that cannot be attributed to chance. If Euclid finds significant deviations from homogeneity, if structures like Quipu turn out to be the tip of a hierarchy that extends to scales our models cannot accommodate, the implications would not be merely cosmological, they would be foundational. The Friedmann equations, which describe the expansion of the universe and from which all of modern cosmology derives, assume exact homogeneity and isotropy. Deviations from that assumption, even small ones, propagate through the equations in ways that can shift every derived cosmological parameter. The age of the universe, the dark energy equation of state, the Hubble constant, by amounts that depend on the magnitude and scale of the deviation. The cosmological principle is not merely an aesthetic assumption about the universe's simplicity. It is a load-bearing wall in the theoretical structure of physics, and the question of whether that wall is more cracked than we have acknowledged is now, for the first time, empirically accessible at the required precision. There is a fourth complication that deserves explicit mention, because it runs beneath all the others and connects them. The question of feedback. The cosmic web is not a static structure, it evolves, and the galaxies within it do not merely respond passively to the web, they affect it. A massive galaxy at a filament node, once it forms, begins to inject energy back into its surroundings, through stellar winds, through supernovae, and above all through the jets of its supermassive black hole, which can pump enormous quantities of energy into the surrounding intergalactic medium over timescales of hundreds of millions of years. This feedback, AGN feedback, in the technical language, changes the density and temperature of gas in the filaments adjacent to the galaxy. It can heat the WIM, making it even harder to detect. It can suppress the flow of cold gas along filaments, starving the galaxy of the fuel it needs to continue forming stars. It can, in the most extreme cases, expel gas from the filament entirely, depositing it in the surrounding void. Understanding the magnitude and spatial extent of AGN feedback on the cosmic web is essential for any precise measurement of the missing baryons, for any accurate model of galaxy evolution, and for any reliable calibration of the web's statistics for use as a cosmological probe. The fact that Tornotti's filament connects to active AGN is, in this context, both a blessing and a complication. A blessing because the AGN illumination makes the filament gas glow brightly enough to see. Without the AGN radiation field, the Lyman alpha photons from the filament might not have been detectable even with 150 hours of Muse time, a complication because it means the gas properties measured in that filament are almost certainly not representative of a typical filament. The AGN are heating the gas, photoionizing it, potentially driving winds into it. The typical filament, somewhere between a pair of quiet, non-active galaxies, looks nothing like what Tornotti's team imaged. The first filament photograph is, in a very real sense, a photograph of the cosmic web on its best behaviour, illuminated and therefore rendered visible by the very AGN activity that makes it non-representative. This is a known limitation and the team was explicit about it. Future campaigns to image filaments in more typical environments, away from AGN, in quieter regions of the web, are technically harder because the gas does not have a bright ionizing source to make it glow. Muse may be capable of detecting the faintest end of this emission in the very deepest observations, but it will require campaign-scale commitments of telescope time that rival or exceed 150 hours already invested. The next generation of extremely large telescopes, the 39-metre Extremely Large Telescope ELT, currently under construction at Cerro Armazones in Chile, which will have an ELT Harmony spectrograph with 15 times the collecting area of the VLT, will transform this problem. With ELT, observations that required 150 hours on the VLT might be achieved in 10 hours. The statistical sample of directly imaged filaments could expand from single digits to hundreds over the telescope's first decade of operations. ELT's first light is expected in 2028. The first scientific results from its spectrographs are expected to begin flowing within a year or two thereafter. The timeline for the first statistical sample of directly imaged cosmic web filaments is therefore not a decade away. It is perhaps 5 to 7 years away, within what is, by astronomical standards, an eye blink. And threading through all of these complications, the missing baryons, the dark matter mystery, the homogeneity question, the feedback problem, is a current of something that I think is genuinely underappreciated in the standard popular science framing of this subject. The cosmic web is not merely a problem to be solved, it is a record. It is the most detailed physical record in existence of the very first moments of the universe's life, written in the language of gravitational dynamics across the largest available canvas. Every filament length, every void diameter, every cluster mass distribution, every galaxy environment correlation carries information about the initial conditions of the Big Bang, amplified and made legible by 13 billion years of gravitational evolution. Read it correctly and you read the universe's birth certificate. Miss something in the reading, and you build models on a foundation with cracks you cannot see. The history of cosmology is a history of people who thought they had read the record correctly, followed by people who found errors in the reading. We are not at the end of that history. We may, with the tools we have built and are building, be at a genuinely decisive chapter of it. The most detailed map of the cosmic web ever produced was published on the 11th of May 2026. By the time you are reading or hearing this, it is already being superseded, not because it was wrong, it was not wrong, but because the instruments that produced it were designed as pathfinders for larger, more ambitious surveys that are already underway or already planned. The map published in May 2026 is a beginning. What comes next is the reason we were building toward this beginning for the last 30 years. The Euclid Space Telescope, currently in its wide survey phase, will complete its primary mission by approximately 2029. The sheer statistical weight of 1.5 billion galaxy positions, measured to redshifts up to 2 across 1/3 of the sky, will produce constraints on the cosmic web's statistical properties, its power spectrum, its topology, its void statistics, that are orders of magnitude more precise than anything currently available. Euclid's primary cosmological targets are dark energy and the growth of cosmic structure, two measurements that are deeply sensitive to both the geometry of the universe and the distribution of dark matter. The cosmic web, in Euclid's data, will be visible not as a feature to be studied, but as a precision measuring instrument, its patterns encoding the values of the cosmological parameters that define the universe. The SCORE, the Square Kilometre Array Observatory, is currently under construction across two sites, the SKA Low Array in the Murchison Radio Astronomy Observatory in Western Australia and the SKA Mid Array at the Karoo site in South Africa. When complete, the SKO will be the world's largest radio telescope, with a total collecting area of more than 1 square kilometre and a sensitivity that will surpass every previous radio observatory by factors of tens to hundreds. For cosmic web science, the SKAO's most transformative capability will be the detection of the 21 centimetre hydrogen line at very high redshifts, the signal from neutral hydrogen gas in the cosmic web before the epoch of reionization, when the first stars and galaxies were switching on and transforming the universe's gas from neutral to ionized. This is the era of cosmic web formation, the era when the initial dark matter scaffold was still assembling, when the first galaxy overdensities were first appearing, when the voids were first opening. No telescope has ever mapped this era. The SKO will, the Simons Observatory and CMBS-4, the next generation of cosmic microwave background experiments, will measure the CMB at resolution and sensitivity sufficient to detect the kinetic Sunyaev-Zeldovich effect from the warm-hot intergalactic medium. The KSZ effect is a tiny distortion imprinted on the CMB as it passes through hot electrons in the WM. Electrons moving relative to the CMB rest frame that leave a frequency-shifted imprint whose statistical properties can be extracted from CMB maps with sufficient sensitivity. The detection of the upper WIM through the KSZ effect would be the most direct thermal measurement of the missing baryons yet attempted, and CMBS-4, expected to begin observations in the early 2030s, is designed to make it. And running through all of these future observational programs is the FRB thread, the KIME telescope in Canada, the Deep Synoptic Array in California, the Meerkat Array in South Africa, and the planned Burst T Array in Taiwan are all dedicated to detecting and localizing fast radio bursts at increasing rates. The current catalogue contains a few hundred localized FRBs for which the host galaxy has been identified and the redshift precisely measured. Within 5 years, that number is expected to reach tens of thousands, with tens of thousands of FRBs sampling the intergalactic dispersion measure along tens of thousands of independent sightlines through the cosmic web. The statistical reconstruction of the web's baryon distribution becomes, for the first time, genuinely achievable, not as a map of individual filaments, but as a statistical reconstruction of the web's bulk properties, the average baryon density in filaments, in sheets, in voids, as a function of redshift, with precision sufficient to test whether the WIM accounts for all the missing baryons, or whether some fraction of ordinary matter remains unaccounted for even after that correction. And then there are the questions we cannot fully articulate yet. This is, I think, the most honest and also the most exciting place to end a scientific narrative. Not with the questions we know are open, but with the acknowledgement that every major discovery in the history of science has brought with it a new category of question that could not have been formulated before the discovery was made. The first maps of the galaxy distribution did not merely confirm the web's existence, they revealed its specific topology, which then raised entirely new questions about what determines that topology. The first direct image of a cosmic filament does not merely confirm the web's gas content, it shows for the first time the boundary between the intergalactic gas and the interstellar gas, which raises entirely new questions about how that boundary forms, how it evolves, and what physics operates in the transition layer. The Cosmos Web Map does not merely show the cosmic web at high redshift. It shows that galaxy properties were being shaped by their cosmic web environment within the first billion years of the universe's existence, which raises the question of what happened before that. Was there already a proto-web during the epoch of reionization? And if so, was it already shaping the first galaxies when they formed? The answer to that question is almost certainly yes. The dark matter scaffold was in place long before the first stars lit up, but we have never seen it at those early epochs. We have never mapped the proto-web. That is the next frontier. And it requires the next generation of instruments. JWST has already shown that it can detect structure at redshift 7. Whether it can detect structure at redshift 10, 15, or beyond, whether the first galaxies, forming in the first few 100 million years, already show the environmental signature of an incipient cosmic web, is one of the most actively pursued questions in observational cosmology today. There is also the question of what the web's future holds. The superstructures found by Boehringer's team, Quipu, Shapley, Serpens Corona Borealis, Hercules, Sculptor Pegasus, are not permanent. They are, as the paper noted, transient configurations. The universe is expanding, accelerating under the influence of dark energy, and as expansion proceeds, the gravitational binding of the superstructures will eventually be overcome. On timescales of tens of billions of years, the superstructures will break apart into smaller, independently collapsing units. The cosmic web's filaments, on the very largest scales, will thin and dissolve as the universe expands. Void regions will grow. The topology of the web will change. We cannot observe that future. But we can observe the past of other regions. By looking at progressively higher redshifts, we see the web at earlier and earlier stages of its assembly. The Cosmos Web Map traces it to 1 billion years after the Big Bang. Future surveys with ELT and SKO will push it back to 200 or 300 million years, within the epoch of first galaxy formation. Piece by piece, we are assembling the web's biography. How it formed, how it grew, how it shaped the matter within it, and how it will eventually, billions of years hence, dissolve into the expanding dark. But for now, for this moment in the history of science, the achievement is real, and it is extraordinary. After a century of theory and a half-century of indirect observation, and 3 decades of progressively more ambitious mapping, we have, in the span of 18 months, photographed a cosmic filament for the first time in history, discovered the largest known structure in the universe, and built the most detailed map of the large-scale structure ever made, reaching back to within 7% of the universe's current age. 3 separate teams on 3 continents using 3 different instruments, converging on the same hidden architecture of existence and making it for the first time truly visible. This is the beginning of the era when we can actually read the cosmic web, not just trace its outlines through the positions of galaxies, but measure its gas, map its dark matter, trace its influence on the galaxies within it, and extract from its statistics the imprinted signal of the universe's very first conditions. We are in 2026 at the threshold of cosmic cartography at full precision. What we find on the other side of that threshold will almost certainly surprise us. The history of this subject makes that prediction with something close to certainty. Every time we achieved sufficient precision to test our models at the next level, the models held and then surprised us in some specific, precisely located way. The surprises are not random, they are clues. They point consistently toward physics that is slightly richer, slightly more complex, and slightly less like our assumptions than we had believed. The cosmic web, when mapped at sufficient precision, will do the same. The question is not whether there is more to discover. The question is only how long it will take to see it. There is a moment, in the very deepest observations made with the Very Large Telescope, when the software finishes stacking its hundreds of hours of data and renders for the first time an image that was previously inaccessible to any human eye. The astronomers call this seeing into the noise, reaching below the level of background fluctuations to find the signal that was always there, waiting beneath the surface of the sky. I keep coming back to that phrase when I think about the cosmic web. The signal was always there. For 13.787 billion years, the web has existed. It was there before the Earth formed. It was there before the Sun formed. It was there before any star in any galaxy, anywhere in the observable universe formed. It was there when the first hydrogen atoms coalesced in the cooling aftermath of the Big Bang and gravity began very slowly to draw them together along lines determined by quantum fluctuations so small that they operated at scales billions of times smaller than an atom. It has always been the framework. It has always been the reason matter has the distribution it has. We simply could not see it. Every civilization that has ever looked up at the sky has looked up at a sky organised at scales beyond imagining by this invisible web. Every ancient astronomer who traced the movements of stars across the dome of heaven was moving through a universe whose deepest structure was a filamentary architecture they could not have conceived. Every cosmologist of the 20th century who argued about whether the universe was smooth or lumpy was arguing about a web they could not yet photograph. Every simulation run on every supercomputer since the 1980s has been an attempt to recreate, in mathematics, a thing that was already there in the data, waiting, faintly, for instruments precise enough to find it. There is something in that waiting that speaks to the particular quality of what science is. Science is not the act of discovering things that were hidden. It is the act of building the eyes required to see what was never hidden, only inaccessible. The cosmic web did not conceal itself. It could not. It had been glowing faintly for billions of years. We were simply not listening carefully enough, for long enough, with instruments sensitive enough to hear it. David Tornotti listened for 150 hours, and the universe answered. Hans Boehringer catalogued 30 years of X-ray data and named the largest thing that has ever been named. Hossein Hatamnia and Bahram Mobasher built a pipeline that turned 164 zeros and galaxies into a map of 13 billion years of cosmic architecture. Thousands of scientists before them built the telescopes, wrote the software, designed the detectors, argued about the theory, and spent careers chasing evidence for a thing they could not yet prove. Vera Rubin measured 60 galaxy rotation curves to make dark matter undeniable. Zeldovich filled notebooks with equations about pancakes collapsing in the dark. 50 years before anyone could check his work. This is how science actually moves, not in single eureka moments, but in accumulations, each result building on the last, each instrument extending the reach of the previous one, each generation of scientists asking the same question with better tools than the generation before, and finding that the answer is slightly more complicated and slightly more extraordinary than they expected. The cosmic web is not finished revealing itself. The missing baryons are still missing. Dark matter is still undetected. The homogeneity of the universe at the largest scales is still uncertain. The first protoweb, forming in the dark before the first stars, is still unmapped. These are not failures. They are the inheritance that this generation passes to the next. The open questions that make the next generation of scientists necessary. There is a phrase cosmologists use that I have always found quietly profound. The universe is not obligated to be simple. It is not built to fit inside our models. It is not arranged for our convenience. It is arranged according to its own logic, which we may approach with mathematics and instruments and extraordinary patience, but which we do not control and cannot fully anticipate. The cosmic web is the universe's logic made visible at the largest scales. The physical record of 100 quantum fluctuations from an inflationary period we cannot directly observe, amplified by gravity over 13 billion years into a structure larger than imagination. We have, in the last 18 months, finally begun to read it. What it says, in the end, is this. The universe spent 787 billion years building the conditions for something like us, to stand in something like a valley on something like a planet, and ask why things are the way they are. And the answer to that question, it turns out, begins not in biology or chemistry or geology, but in the shape of dark matter 13 billion years ago, in the specific pattern of a web that was already in place before the first atom of hydrogen was pulled into the first star. We are not separate from the cosmic web. We are an expression of it. The carbon in your body was forged in a star that formed at a filament node, fed by gas that flowed along a dark matter thread from a void where it had been gathering for billions of years. The iron in your blood was scattered across a filament by a supernova whose progenitor star inherited its position in the web from the quantum noise of the first second. You are, in a very precise and not merely poetic sense, a locally complex arrangement of matter that the cosmic web built. The question I am left with, the one I find I cannot put down after all the reading and all the research and all the images of purple filaments glowing against Hubble backgrounds, is not about what the web is. We know, broadly, what it is. It is the question of what the web means, in the sense of what its existence says about the kind of universe we inhabit. A universe that began undifferentiated and isotropic, and organised itself, through gravity and dark matter and time, into this intricate, evolved, specific pattern, a pattern that contains somewhere within it us. Why this pattern and not another? What determined the specific spectrum of initial fluctuations that produced these filaments and these voids and these superstructures? Was there a pre-inflationary physics that constrained those fluctuations, or was the pattern the result of pure quantum chance? One roll of the dice among an infinite number of possible universes, each with its own web, its own topology, its own eventual galaxies. We do not know, we may never know, but we are at last reading the dice in enough detail to begin asking the question precisely. That is enough. That has always been enough.